as you can see, I'm not making each of the podcasts of the same length just because the flow depends on which topic we are discussing. Plus, I got this new contraption headphone so that I can move my hands. The other one was not very good for that. Nonetheless, continuing with the temperature and density variations in the ocean, we talked about the halocline, where there is a sharp gradient in salinity below the surface. Similarly, you have something called a pycnocline, which is a sharp gradient in density change, and you have a thermocline, where the temperature has a abrupt drop from the surface to the depth. So we are looking here at a low latitude temperature profile and a high latitude temperature profile, a low latitude density profile and a high latitude density profile. So as you can imagine, low latitude is a very generic term, and high latitude is basically where you are going into very cold temperatures where the ocean is going to be very well mixed, so that the stratification happens only in some seasons when the heating happens near the surface, right? So in the low latitudes, you can see that the average temperature is 24 degrees depending on where you are, and there is again this well mixed layer. It's called the surface mixed layer because of the heating, the cooling, and the winds that are churning the ocean constantly. And then you have a very sharp drop in a very short distance from 23 degrees down to almost 4 degrees, so that happens in just about a kilometer. Below that you have nearly constant temperatures all the way to the bottom of just about 0 degrees centigrade. Sometimes it can be colder depending on where you are, right? In contrast, at high latitudes, the surface is so cold and the densities are so high that the entire water column has been mixed up. So the salt stratification may or may not be there, but density stratification, you can see here, is just like temperature, nearly constant all the way to the bottom. This is kind of an average for the year. We'll see later on when we look at biology that when sun comes up over the horizon, even at high latitudes, for a few months you might get warmer surface and this kind of stratification. This is what we call stratification. So even though we are showing a sharp gradient of temperature, there are temperature scales, which means density scales. So if you look at the low latitude density here, lightest waters obviously have to be near the surface, otherwise they would sink, and the density increases in the same range where the pycnocline, where the thermocline and the halocline are. So the pycnocline has got the sharp increase in density from below the surface mix layer all the way to the bottom of this, sometimes called the seasonal thermocline and so on, but we will come back to that a little bit later on. So you can see that the density is going from about 1.02 or so to 1.02728 and so on. So these, if you draw many horizontal lines in the pycnocline, you can create density ranges, which we call isopycnals or constant density layers. This stratification, it turns out, is very important. If you have a system that's rotating like Earth and you have stratification, then they place a lot of constraint on how the flow can get organized, how turbulence can make a difference in a stratified system is very important. We won't get into too many details, but just remember that stratification is a huge constraint on the flow. The pycnocline is basically absent at high latitudes, corresponding to this lack of thermocline. So the density is high from the surface all the way to the bottom. So the ocean is layered, and we have three distinct layers on average in general. Mixed surface layer, which is above the thermocline, which is called the constant density layer. There are details. Horizontal density gradients make a difference, even though vertical density gradients may be very low. The upper water, which is in the thermocline and pycnocline, and the thermocline is not fixed. With the season, the warming may penetrate deeper, the thermocline may get sharper and deeper, winter, when the cooling happens, the mixing may penetrate deeper, and again, thermocline may sharper and thinner, and so on and so forth. There is a seasonal thermocline that also happens. And there is the deep water where the density and temperature are nearly constant, and we saw that the salinity is also nearly constant, right? These layers matter because life gets organized based on this, based on availability of light, availability of food, oxygen, and so on and so forth. At high latitudes, you basically have an isothermal ocean, nearly constant temperature, well mixed, no layering, and it's nearly isopycnal because the density is nearly constant all the way to the bottom. Let's look at some very interesting properties that you get, as I mentioned, because of this non-linear density change with salinity and temperature. Two things to notice: when you are at warm temperature, here there is a change of 5 degrees in temperature. In warm temperatures, the density goes from 1.0235 to 1.0247, so the change of 0.0012, whereas at cold temperatures, the same 5-degree change is only giving you 0.0004 in density change, right? So the non-linearity, these lines of constant density based on temperature salinity, are not linear, they are curved. This makes for another interesting thing. So imagine you are on this constant density line of 1.024, okay? So you take the water mass here, which is at the same density but has a salinity in this range and the temperature in this range, and you take another water sample from the same density as one here, but now the temperature is in the 5-degree range and salinity is much fresher in the 31-degree range, and then you mix it. Okay, same density, different salinity and temperature, and you're going to mix them. You're going to get average temperature, average salinity, which is actually going to end up being somewhere here. Okay, you're mixing this salinity and get a different salinity. You're going to mix this temperature and get a different temperature. So even though you are mixing two water masses with the same density, because of this non-linearity, you're going to end up with a different density altogether. Magically, by mixing two waters of the same density with different salinity and temperature, you're going to produce a second density. This is called cabbeling, C-A-B-B-E-L-I-N-G. Not a very big phenomenon, but it can matter in some places where such mixing can happen. So this is the impact of non-linearity of seawater density on temperature and salinity. Something we have to remember makes for lots of interesting flow features where you're mixing warm, fresh river water with cold, saline ocean water and so on, and how you can create density-driven circulations. Okay, so we'll learn a bit more about that later on.